Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 1.4 from your textbook, which is our first introduction into an actual technique for solving differential equations. So far, our focus has been trying to sort of develop a language or vocabulary to talk about differential equations, setting up some general theory for solving differential equations and solving initial value problems. We learned a couple existence and uniqueness theorems, one that applies to any order linear differential equation and one that applies to any first order differential equation. And then we also spent a little bit of time trying to learn about visualizations that allow us to understand solution curves to differential equations without needing to solve them. Now that we've done all that sort of general analysis, now we'd like to actually take a little bit of time to learn how to explicitly solve different types of differential equations. In Chapter 1, our focus is going to be learning some different techniques for solving first-order differential equations. At the very end of Chapter 1, we'll talk about some ways that we can extend the techniques that we learned for first order to some very special cases of higher order differential equations. And then it won't be until the very sort of end of our course that we'll return to talking about solving higher order differential equations. And that's really because we need some mechanisms from linear algebra to understand how to solve higher order ones. So for now, pretty much everything we're going to be talking about are different techniques that apply to solving first order differential equations. Generally speaking, what we're going to do in each of these sections is basically come up with some different types of first-order differential equations and learn an approach or technique that works on that specific type of differential equation. So our first one here, which is sort of the most basic, is what is called a separable differential equation. So we have a definition here. A first-order differential equation is said to be separable if it can be written in this format, which is that you have a function of y times y prime equals a function of x. So does this mean that every first-order differential equation is separable? Absolutely not. This is a specific format that if you can write a first-order differential equation into this format, then we consider that differential equation to be separable. Why is this a format that we sort of are interested in, or why are we going to study this? Well, you can see that it sort of is a very sort of simple format. It's basically saying that even though you have both a function of the dependent and independent variables, you can separate them into two separate functions. In other words, they're not mixed together. You can actually separate them as functions. And the reason that we begin our analysis of first-order differential equations with these separable ones is that we have a very easy way of solving these. So we have this theorem here that explains how to solve any separable first-order differential equation. So this says, suppose you have a separable first-order differential equation that is in this form, g of y prime equals f of x. Then, provided that g of y and f of x are both continuous, so in other words, as long as both of those functions are continuous on the interval that you're working in, then the general solution, general solution, remember, means that every solution can be written in this format, to this differential equation is given by integrating that g of y function dy and setting that equal to the integral of that f of x function dx plus an arbitrary constant. So notice that what this is basically saying is that if you can separate the function of y and the function of x, then you can integrate each of those with respect to their individual variable, and that'll give you the general solution. Now, once we've established this theorem, then this basically tells us that to handle solving separable differential equations can be very easy. We write it into this format and then integrate on each side with respect to the variable on that side. But we do need to prove why this actually works here. So the proof is not particularly hard, but it can be a little bit just sort of hidden. Your book sort of just says it's via the chain rule and leaves it at that. But I'd like to just give a little bit more in depth so that you guys can sort of see how this works. So to do this, we're going to use a little bit of notation. We're just going to let g of y, capital G of y, be equal to that integral of g of y dy. So in other words, we're letting that capital G be the antiderivative of that little g of y function. And we're going to let capital F of x be equal to that integral of f of x dx. So what we need to show, in other words, just with this new notation, is we need to show that capital G of y equals capital F of x plus c is solution to g of y, y prime equals f of x. So we basically need to show that that really is going to be the solution to this differential equation. So how do we show that? Well, what we're going to do is we're going to differentiate this equation. Now, you can differentiate, you can always apply differentials on both sides, but the thing you need to do is you need to make sure you differentiate with respect to the same variable. So as our proof here, what we're going to do is we're going to take the derivative with respect to x on both sides. So the derivative with respect to x of g of y, and that's going to be equal to the derivative with respect to x of f of x plus c. All right. What does this tell us? Well, let's actually focus on this right-hand side first. This will be a little bit easier. We know that the derivative is going to apply to each piece separately. So this is going to become f prime x, right? And then, of course, the derivative of that c is going to be 0. And so we have the derivative of capital F of x. Well, what is the derivative of capital F of x? Well, if f of x is equal to the integral of f of x dx, well, then the derivative of that, since capital F of x is the antiderivative, this derivative has to just be little f of x. I mean, that's what it means to be doing an indefinite integral or saying something is the antiderivative of a function. What about on the left-hand side? Well, we're taking the derivative with respect to x of a function of y. And remember, always when we're working with this, we're thinking about y as the dependent variable. So y depends on x. So to apply this derivative here, you have to do this as a chain rule. So you have to differentiate the outside function, which is at g. So we would get g prime of y. And then you'd have to differentiate that inside, which is y as a function of x. So we get times dy dx. That's just chain rule, right? You differentiate the outside function and as normal, and then you differentiate the inside because we're thinking about y as a function of x. Okay, but what can we say about this? G prime of y. Well, if we think about that, that's the derivative of the antiderivative of g of y. So this is just going to become g of y. And of course, we know notationally dy dx is the same as y prime. I mean, those are just different notations. So we get that. What do we notice here? Well, we notice that then this expression after differentiation gives us the equation that we're trying to solve. So that's exactly what we wanted. So this tells us, so g of y equals f of x plus c is solution to g of y, y prime equals f of x. Check. So we've proven this, right? We've proven that if you take the integral of g of y dy and the integral of f of x dx, then the general solution to your separable differential equation is going to just be the integral of g of y dy equal to the integral of f of x dx plus c. Again, when you guys are doing this, you don't need to use this antiderivative notation. I only use that to do this proof so that it's a little bit clearer why this actually works and so that you guys can see the chain rule that happens on the left-hand side. But overall, when we're actually solving separable differential equations, our main strategy is going to be to put it into this format and then immediately go to these integrals where on the left-hand side you're integrating with respect to dy and on the right-hand side you're integrating with respect to dx. All right, last quick comment I have before we get into some examples here. Just being aware that in your textbook and also just in stuff that we're doing, sometimes we do switch between the two notations for derivative. Sometimes it is convenient to use that y prime notation, the prime notation for derivatives. And sometimes when we're being very careful about what we're differentiating with respect to, we will use this dy dx notation. They mean the same thing, but we'll just be comfortable switching between those two notations depending on the situation. Your textbook also writes problems that make use of both dy dx and y prime interchangeably, so just be aware of that. All right, let's get into some examples of solving separable differential equations. All right, so for our first example, we want to try to find all solutions to the differential equation y prime minus sine of x over e to the y to equal 0. Now, again, as we investigate further into differential equations, we will run into differential equations that are not separable. So we're not saying that every differential equation is separable. But right now, this is the only technique we've learned, so this is the one we're expecting to use. So let's see how we would do this. So we need to get it into that format. So we can start to work on this. This is an equation, so we can bring that sine of x over e to the y onto the other side. Notice that you can sort of see why this is separable. It's not in that separable format just yet, but you can sort of see that the function of x and the function of y are in separate pieces. So we can, in other words, bring everything that's in terms of y onto the other side by multiplying. So we can get e to the y prime equals sine x. Now we can use that theorem that says, okay, this is in our format. There's our g of y. There's our y prime. There's our f of x. So the function of y is over here. Function of x is over here. So we can move to the step of saying what the solution is going to look like. So it's going to look like the integral of e to the y dy is going to be equal to the integral of sine of x dx. So we integrate here with respect to y, and we integrate here with respect to x. We know how to integrate both of these. This is going to become e to the y. And on this right-hand side here, we know that that integral is going to be negative cosine of x. And you could technically put the constant of integration on either side. One constant, you only need one, because if you put a plus c here and a plus c, c1 here and a c2 here, well, then you could just combine the constants of integration and make a new constant. So in general, we only put the constant of integration on the independent side. So we put plus c here. So there we go. That's our general solution. Now, this is what we would consider like an implicit form of the solution, and we don't really care too much in this class about implicit versus explicit, but notice that it would be pretty easy in this situation to go ahead and actually just get a nice explicit form for y. We could apply the natural log on both sides and get that y is the natural log of negative cosine x plus c. And the reason I want to just take the time to write this out in this situation, it is a good habit that if it's easy to put something in an explicit form, you should. We prefer explicit forms, but it's not always easy to do that. I mean, if this had been a function over here of y that's hard to invert or something, we might want to avoid it. But what I really want to call your guys' attention to is that notice that when you apply that ln, you don't have the plus c still sitting outside. The ln applies to this entire side, so that constant of integration is now inside that natural log. And in a lot of ways, as we do more examples of this, this is why when you guys were in like a 191 class or anytime you sort of learned about integration, you were constantly stressed to add that plus c onto your indefinite integrals. And that's because that constant of integration is so important in getting the general solution, and its presence also can be impacted if you continue to sort of rewrite the form of your answer. So in this case, that plus c doesn't end up just being outside, it's actually inside the logarithm because we wanted to solve for y overall. Notice that in this technique here, right, all solutions can be found in this format. Right, so there are no other possible solutions. Every solution is going to be in this format. So just as a side note here, this is an example of a general solution. Every solution to this differential equation can be written in this format because that's what our technique does for us. So if we can put it into this separable format, then this separable format automatically has all solutions in this format, which we call a general solution. All right, let's go ahead and take a look at another example. And in the next one, what we really want to pay attention to is how we have to be very careful along the way of putting things into this separable format. In this case, it was very easy because all we needed to do was bring this to the other side and then do a multiplication. But there are some operations that can be a little bit dangerous. So let's go ahead and take a look at an example of that. So for this example, we want to try to find all solutions to this differential equation. X squared plus 1 times y prime minus y squared equals 0. So again, our goal at the beginning, since we only have one technique, is to see how we can separate this. So we can start by doing x squared plus 1 times y prime is equal to y squared. Okay, so we want to get that by itself. And then notice that we can sort of isolate the y prime by dividing by x squared plus 1. Y prime equals y squared over x squared plus 1. Now, dividing by variables is always pretty risky. In this case, dividing by x squared plus 1 is not a big issue because x squared plus 1 can never be 0. Actually, as we investigate further in this class, dividing by anything that's in terms of the independent variable is not a big concern. Because even if there were situations where this x squared plus 1 could be 0 and you divided it over, those are only domain issues. In other words, they would only impact the interval for which the solutions would make sense. So we're not really concerned about dividing by things that involve the independent variable, but we will need to be very cautious about dividing by things for the dependent variable. Notice, though, that's exactly what we need to do next. To finish separating here, we need to bring this y squared over here by division, and that does have the potential for a divide by 0. So let's go ahead and carefully write that out. We can say 1 over y squared, y prime, is equal to 1 over x squared plus 1. That's dividing by that y squared. But that is, of course, under the assumption that y squared is not equal to 0. In other words, it's under the assumption that y is not 0. So after we finish this up, and we're going to do some more work here, we'll have to come back and consider the situation where y is 0, because our work from here on out is under the assumption that y is not 0. All right, at this point, though, this is nice and separated, so we can go ahead and use our theorem and say that this is the integral of 1 over y squared dy, and it's going to be the integral of 1 over x squared plus 1 dx. So again, because you can separate, you can integrate the function of y dy and the function of x dx. On this side over here, integral of 1 over y squared, well, you can think about that as y to the negative 2. And if you integrate that, you should get negative 1 over y. On the right-hand side here, you should get arctan of x and then plus c. And again, constant integration generally goes on the side with the independent variable. All right, can we unpack this and actually get an explicit form for y? Sure, we can multiply by negative 1 first. So we get 1 over y, negative arctan of x. Now for a little bit of a weird thing, negative c, but remember c is just an unknown constant. So c, negative c, it's just still a constant. So we can actually leave this as plus c. Now, sometimes in some texts or some online resources, what they do is every time they do a manipulation like that, they rename the constant. So this guy might become like C1 now, but it's still just an unknown constant. It's the negative of the original unknown constant, but it hasn't really changed formats. So for us, the sort of most elegant solution is just to keep calling it plus C because it's still just a constant. Now we'd like to get this y out of the denominator, so we can do the reciprocal on both sides and get y equals 1 over negative arctan of x plus c. And now notice that that plus c is now in the denominator because we performed the reciprocal. So there we go. There's a nice, clean, explicit form for our solutions. Is this everything, though? Well, no, because this is working under the assumption that y is not equal to 0. So we need to go back and we need to see what happens when y is 0. So let's go ahead and take this over here. So we need to do a check. Y equals 0. So what happens if y is 0? Well, we can just manually check if y equals 0, is that a solution? Well, on the left-hand side, if we plug in y equals 0, its derivative is going to be 0 as well. So we would get x squared plus 1 times 0 minus 0 squared. And if we multiply all that out, you're just going to get 0. On the right-hand side, we also have 0. So notice we're going back and checking in the original equation. It doesn't make sense to check in anything after we divide it because the division over here is assuming y is not 0. So you always want to go back to the original equation. And that works, right? That left-hand side equals that right-hand side. Check. So y equals 0 is a solution. Actually, you guys would call this like an equilibrium solution because it's a solution of the form y equals a constant. In this case, the constant is 0. So what does this tell us? Well, this tells us that this is an example of a differential equation that does not have a general solution because we have solutions of this format, but we also need to list this one single solution, y equals 0. So our solution set here would be y equals 1 over negative arctan of x plus c. So anything of that form, that's an entire family of solutions. So that's things like 1 over negative arctan plus 1, 1 over negative arctan plus 100, 1 over negative arctan minus 17 pi, whatever, right? Anything of that format with a constant there, those are all solutions. But we also have this one particular solution, y equals 0. So this is our solution set. This means that this is an example of a differential equation that does not have a general solution. Remember, having a general solution means that everything fits one single format, and that's simply not the case here. How do we know that there's no way to get y equals 0 in terms of this format? Well, just think, are there any choices of constants where this is going to reduce to y equals 0? And of course the answer is no, because this is a fraction with 1 in the numerator. It's impossible for it to be equal to 0. So there's no way to phrase this y equals 0 in this format. So the solutions are everything of this format along with this y equals 0. Notice that this tells you guys that anytime you're working with differential equations, separable or anything that we talk about later on, anytime you divide by the dependent variable or a function that involves the dependent variable, like we did right here, you're going to have to be very cautious about whether or not that introduces some additional solutions. All right, let's go ahead and take a look at a couple more examples that sort of flesh out that idea a bit more. All right, so we're going to try to find all the solutions to this differential equation. So we have y minus 4 times y minus x times y prime equals y minus 4 times y minus x times y. So let's see what happens when we do this. So it shouldn't be too hard to see that maybe the first thing we want to do is divide both sides by y minus 4 to remove those factors. So let's do that. We get y minus x times y prime equals y minus x times y. Now, to do that division and cancel out those y minus 4s, we are working now under the assumption that y is not equal to 4. So we'll have to go back and check that later on once we've sort of finished. All right, there's another cancellation. We could go ahead and cancel y minus x on both sides by dividing by y minus x. So if we did that, we would get xy prime equals y. And of course, that's working under the assumption that y minus x is not equal to 0. So we'll have to also consider that. That's the whole point of this example, to be honest, guys, is just to show you what happens when you have multiple things you sort of need to consider. All right, at this point, we can start to see how we might need to separate, but unfortunately things are on the wrong side, so we need to divide the x over. So let's do that. Y prime equals y over x. Should we make a little note, x not equal to 0? Yeah, if we were being incredibly thorough, we would. But of course, again, if x is 0, that would just be a domain consideration, which is not really our focus in this class. So again, if you wanted to be super thorough, you could make a note, x not equal to 0, and have that be a limitation on the domain. But again, that's not my point of emphasis in this class. I'm more interested in finding the solutions, not worrying so much about where they make sense. We're just going to take the assumption that we're only working with these things in sections where they would be well defined. So we're not going to make any note here about x not equal to 0 because, again, that's just about the independent variable. However, if we divide this y over, that is something we'll need to consider. So then we would get 1 over y prime is 1 over x. And that one I do want to make a note of, that's y not equal to 0. So again, notice that all of these are things that we're taking the time to mention because they involve the dependent variable, which is basically the solution we're looking for. Okay, at this point, this thing is separated, so we can use our theorem to actually solve it. Integral 1 over y dy is the integral of 1 over x dx. So it should be pretty clear there. We're going to get ln absolute value y there equals ln absolute value x plus the constant. Now we can try to go ahead and unpack this thing. So we can try to remove this ln by raising both sides as powers of e. So we get e to the ln absolute value 1 equals e to the ln absolute value x plus c. Notice that that ln x plus c goes up into the exponent there. Okay, what happens here? Well, we have that cancellation. So over here we get absolute value y. And then over here, well, this is a little bit tricky. How do we can't just cancel this because we've got this entire exponent there. So let's rewrite this a little bit by separating this as e to the ln x times e to the c. Because if you have added exponents, you can view that as a multiplication. So that's e ln x and then e to the c. Oh, that looks a little bit weird. That almost looks like c to the c. So let's make sure that's clear. That's e to the c. All right. Same sort of trick here. E to the ln x, we can cancel those, and we get absolute value y equals absolute value x times, okay, e to the c, well, c is an unknown constant. E to a constant is going to be another constant. So again, if you want, you could call that c1, but in our notation, we'll just call that c. And we could rewrite then as absolute value y equals c absolute value x. Now, this is sort of weird because we've got these double absolute values here. Since we have this unknown constant here, we can choose the unknown constant to assure that the absolute values are taken care of. So a standard sort of simplification, and this is something we're going to see several times, so good to just be comfortable with this, right? We can actually reduce this to cx. Now, again, this is actually another redefining of the constant. So this was C1 here. Now this would be actually a C2. And this is just a choice of constant to guarantee that these absolute values are sort of accounted for. Your book goes through a little bit more detailed of an explanation of that. I think it's a little bit outside the scope of our class overall to go through all that. It's just not super necessary. So I'm just going to sort of state that if you guys get an absolute value on both sides with that C there, you can go ahead and just simplify by dropping those absolute values. Okay, so there we go. Solutions of the form y equals cx. So in other words, linear solutions that go through the origin here. We've got some things to check though, so let's go back up and consider each of these things here. So we need to check these. So we'll take each of these, and we'll take this stuff, and we'll perform a little check. Okay, so we'll just check them in the order that we found. So let's check y equals 4. So again, we can imagine plugging that in on both sides. I think it's pretty clear, though, on this one. I mean, because if you plug in y equals 4, you're going to get a 0 there and a 0 there. So the left-hand side is going to be 0. The right-hand side is going to be 0. So this guy is a solution. Y equals 4 is a solution. What does y minus x not equal to 0 mean? Well, if we think about that, that's really y minus x equal to 0. That's really y equals x. So we're really checking y equals x as a potential solution. If we plug in y equals x, again, that's going to be 0, and that's going to be 0 automatically. Of course, the derivative over here would be 1, but it's not relevant because it's getting multiplied by those zeros there. So left-hand side would be 0. Right-hand side would also be 0. So check. Okay, so those ones work. And then finally, that y not equal to 0 there, we'll need to check that. Y equals 0. Well, if y is equal to 0, it should be very clear that the right-hand side is going to be 0. And of course, the derivative of y equals 0 is 0, so the left-hand side is going to be 0 as well. So left-hand side, 0, right-hand side, also 0, check. So all of these things work as solutions. So we would need to say that our solution set is everything in the form y equals cx, also y equals 4, also y equals x, and also y equals 0. Now, this is a pretty complicated solution set, so it's saying anything of this form, y equals cx, and then also this equilibrium solution, this linear solution, y equals x, and this y equals 0, which is another equilibrium solution. This is okay, but to be honest, it's not the best. And the reason is that actually this solution set is a little repetitive. Let's think about this y equals x. This y equals x actually doesn't need to be written again, because this y equals x is actually part of this family here. Right? If we choose c equals 1, remember c is an unknown constant, if you choose c equals 1, you get y equals x. So this right here is actually in that family there. So we just indicate that with a nice little color there, right? This y equals x actually is in here for c equals 1. So is this y equals 0, right? This y equals 0 is actually in there as well if we choose c equals 0. But this y equals 4 is not. The y equals 4, there's no choice of a constant. No matter what constant you choose, you're never going to get y equals 4. You could get y equals 2x, 3x, 5x, square root of 2x, ex, pi x, whatever. You can choose any constant you like, but you can't get y equals 4. So the best way to define this solution set would be to say it's everything of the form y equals cx as well as y equals 4. And this is the ideal way to phrase the solution set, because this says every possible solution without mentioning any repeats. These two things here, which are definitely solutions, actually are contained in this family, so they do not need to be rewritten, and it's actually repetitive to write them like that. Okay, so this one here, there wasn't much to really do in terms of the solving. I really wanted this to be an example for you guys of checking multiple things, seeing whether or not those multiple things were potentially solutions, and then understanding how to write the most simplified form of the solution set. Would we say that this differential equation here has a general solution? No, it does not, because it has this family along with this extra solution, so there is no one format for all of the solutions. All right, let's go ahead and take a look at one final example here. So for this final example, we're going to change gears a little bit, and we're going to go ahead and look at solving an initial value problem. So we're not going to be trying to find all the solutions. We're just going to be trying to solve for the particular solution that satisfies this initial value problem. So in terms of doing this, we're going to start the same. We need to find the solution to this, and then we need to make sure that it fits that initial condition. So from here, right, let's just rewrite for a moment. Y prime equals x squared cotangent of y over x cubed plus y. So you want to go ahead and you want to start by just trying to solve the differential equation, and then we'll deal with the condition at the end there. So first thing we're going to do is we're going to divide that cotangent of y over. So we could get 1 over cotangent of y prime equals x squared over x cubed plus y. Now, we just had that long discussion about being very careful about dividing by functions of the dependent variable, and we just divided by cotangent of y. However, with IVPs, it is much easier to tell whether or not you need to have any concerns. Notice that with our IVP, we're saying, right, that if we take a look at this IVP, we're working at where x is pi over 4 and where y is 1. Meaning, if y is 1, there's no danger that cotangent of y is 0. Cotangent of y being 0 potentially happens when cosine is 0, so that would happen near like 0 or like pi or... if cotangent is 0 when cosine is 0. So that would happen near like pi over 2 or 3 pi over 2 or things like that. So there's no concerns in this case about needing to make a note of like cotangent of y not equal to 0, because we know we're working with near where y is equal to 1. So there's no concerns here about that. All right, so we can just proceed and actually start to do our integration here. So notice that on this side, maybe before we integrate, we might want to recognize that just as tangent. So that's tangent y prime equals x squared over x cubed plus 1. Let's go ahead and integrate. So we get integral of tangent y dy is the integral of x squared over x cubed plus 1 dx. Okay, left-hand side is a little bit messier, but we probably remember that as ln absolute value secant y. And over here, we can do a little bit of a u sub. We can say u equals that x cubed plus 1. Du is going to be 3x squared dx. So it looks like we're going to get a 1/3 du is x squared dx, which is actually what we have there. So this can become the integral of 1/3 1 over u du. So we get ln absolute value secant y. Looks like we're going to get 1/3 ln absolute value u plus c. And then ln absolute value secant y equals 1/3 ln absolute value x cubed plus 1 plus c. Obviously got to undo that substitution in there. Okay, let's go ahead and go a little bit further. We can at least unpack that ln. So we can say that secant of y in absolute value is going to be e to that 1/3 ln x cubed plus 1 plus c. Now we can do that same sort of trick. We can say secant y there is equal to e to the 1/3 ln absolute value x cubed plus 1 times e to the c. Then, of course, we can just redefine that as a new constant. So we can get absolute value secant y is c e to the 1/3 ln absolute value x cubed plus 1. Now, we are tempted to just cancel here, but we have that 1/3 stuck there. So let's put that 1/3 into the natural log as an exponent, right? You can take constants outside of a natural log and put them in as exponents there. So I'm going to just put a little divider bar so we have some space to work on there. So let's take this thing over there. Absolute value secant y is c e to the ln x cubed plus 1 to the 1/3 now. Now we can go ahead and do that cancellation, and we get absolute value secant y is c ln absolute value x cubed plus 1 to the 1/3. All right. At this point, again, we can use that sort of trick and say we've got our constant outside. We can... Oh, we don't have an ln there. Right? Excuse me. Let's just get rid of all that. Sorry. We're canceling out that ln. Excuse me about that. We got our absolute value x cubed plus 1 to the 1/3. Okay. Use that same trick to say if we choose the appropriate constant, we don't need the absolute value bar. So we can say secant of y is x cubed plus 1 c x cubed plus 1 to the 1/3. Okay, so there we go. Now we just need to make sure we satisfy this initial condition. This initial condition says that when x is pi over 4, y is supposed to be 1. So we can go ahead and do that. We can say x is supposed to be pi over 4, y is equal to 1. Yep. So we plug those in and we can solve for the appropriate choice of the constant. So we get secant of 1 is pi over 4 cubed plus 1 to the 1/3, which is pretty horrendous looking because none of this stuff really simplifies. But we can get our constant there. It would be secant of 1 over pi over 4 cubed plus 1 to the 1/3. Delightful, right? That horrendous mess. So what is our actual solution? Is it this constant? No, it's this equation with this constant plugged in. So our actual solution here, we'll just put this right here, solution would be secant of y is equal to secant of 1 over pi over 4 cubed plus 1 to the 1/3 times x cubed plus 1 to the 1/3. There we go. So there is our unique solution to the IVP, right? Which actually gives us not only the solution, I mean, these guys here are the solutions to the differential equation, but now we've found the correct choice of constant given the initial conditions, and we've got our solution there. So the only thing that's, I think, really important about this, I apologize that it's such a messy constant and everything, but again, we're not going to really worry about getting a value for that, so we're just trying to make sure we understand the concept of determining the solution to an IVP. The really important thing, though, in terms of a theoretical idea, is that when working with an IVP, you know what x and y values you're working near. Specifically, you know what y values you're working near. So when you went to solve this moment where you divided by cotangent of y, which would normally pose a concern, we'd have to say, okay, what are the potential y values that are going to make cotangent of y equal to 0? We knew that wasn't a concern because we knew we were near y equals 1. So there was no issue with dividing this over, so we didn't have to worry about anything like cotangent of y not equal to 0, like we were doing if we were trying to find all the solutions overall. In our next video, we'll look at a couple more examples of solving separable differential equations, and we'll also just do a quick discussion now that we've seen some examples of talking about things that have general solutions, things that do not, etc.